Hi, I'm El Sayed Hassan, a senior chief mechanical engineer working offshore. Welcome to my channel, NEGM Marine, where I share real-world offshore engineering knowledge directly from the field. In this episode, we are going to dive deep into a critical system that every marine engineer and offshore operator must master, the sewage treatment plant. Specifically, we will explain the theory, the physical configuration, and the operational requirements of the Hamworthy ST-15C model. As you can see on the title screen of 1.jpg, our goal is all about balancing mechanical reliability with biological health to achieve strict MARPOL compliance. Whether you are preparing for a class survey or troubleshooting a system upset out at sea, this walkthrough will give you the practical and theoretical insights you need. Let's get started. We kick off the first part of our episode by laying down the regulatory foundations. On this slide, as displayed in 2.jpg, we focus on Part 1, Regulations and Physical Profile. To run a compliant vessel, we must thoroughly understand the strict vessel discharge criteria enforced under the International Maritime Organization's MEPC 1555 resolution. We will also examine the physical skid layout and the robust mechanical design that allows these certified units to operate continuously under harsh, unpredictable marine conditions. Understanding the rules and the machinery envelope is your first line of defense against compliance failures. Let's analyze our physical asset profile shown here in 3.jpg. The Hamworthy ST-15C is engineered as a highly compact, skid-mounted unit designed to resist harsh offshore mechanical conditions. Let's break down the configuration into three key areas. First, we have the integrated structural chassis. This heavy-duty, high-integrity coated steel shell is divided internally into distinct biological and chemical cells. This robust division prevents cross-contamination and maintains structural rigidity. Second is component redundancy, which is absolutely vital offshore. The skid mounts dual Gardner Denver G, BH1 side-channel air blowers and WG-driven discharge pumps. This allows us to run seamless duty/standby cycles, ensuring that if one blower or pump requires maintenance, the backup immediately takes the load without interrupting wastewater processing. Third, the system features a dedicated automation hub, a moisture-isolated, localized control panel that coordinates float-level switches for fully automated, hands-off operations. Now that we have covered the physical boundaries and structural components, let's shift our focus to how the system actually processes waste. On this transition slide in 4.jpg, we introduce Part 2, Process Flow and Operation Theory. In this section, we will take a detailed look at the biology and chemistry behind the treatment process. We will trace the path of black and gray water as it is transformed from raw sewage into safe, sterilized, and fully compliant discharge effluent that meets international standards. This slide, shown in 5.jpg, is the core of our biological and chemical discussion. It details the 5 automated, interconnected stages of wastewater treatment inside the Hamworthy unit. Let's follow the flow path together. Stage 1 is inlet screening. Raw black and gray water enter the unit where coarse filters strain out large solids. Stage 2 is the aeration or biological stage. Here, aerobic bacteria consume dissolved organic matter. This biological process relies on a constant supply of oxygen delivered through coarse bubble diffusers fed by our redundant air blowers. Stage 3 is the clarification stage, where gravity allows the heavy biomass, or activated sludge, to settle to the bottom of the hopper, leaving clear effluent overflowing at the top. Stage 4 is the chemical dosing stage. The clear water is dosed with sodium hypochlorite to sanitize and eliminate pathogens, followed by dechlorination if required to protect the marine ecosystem. Finally, Stage 5 is the sludge return. An airlift system recirculates the settled active biomass back into the aeration chamber to keep the biological cycle healthy. To prevent system failures out in the field, we must focus on the 3 pillars of operational excellence highlighted in 6.jpg. Let's discuss how we actively protect this asset. Pillar number 1 is biomass protection. The heart of the STP is its aerobic bacteria. If the crew uses aggressive chlorinated bleaches or standard chemical toilet cleaners in the accommodations, it will sanitize the reactor, killing the bacteria and failing your surveys. You must enforce the use of marine-approved, biodegradable, enzyme-based cleaners. Pillar number 2 is continuous aeration. Aerobic bacteria must have oxygen 24/7. If your blowers trip or are left off for more than 4 to 6 hours, the chamber turns anaerobic. This leads to mass bacterial die-off, terrible odors, and dangerous hydrogen sulfide or H2S risks. Keep those blowers running. Pillar number 3 is fluid and sludge dynamics. Operators should perform daily 30-minute sludge settling tests using a graduated cylinder, targeting a 20% to 40% concentration. Also, visually inspect the hydrolift airlift return daily. A clogged return line causes sludge to overflow into the clean water chamber, resulting in failed water clarity audits. Let's look at the data. On this slide, shown in 7.jpg, we have a comparison table highlighting typical untreated wastewater levels, the maximum legal limit set by IMO MEP 1555, and the target performance of our ST15C unit. For biochemical oxygen demand, or BOD5, untreated levels sit between 300 and 400 milligrams per liter. The IMO limit is under 25, but our ST15C targets a superior performance of under 15 milligrams per liter. For total suspended solids, or TSS, untreated levels of 250 to 350 are reduced down below our target of 20, well below the IMO limit of 35. Fecal coliform bacteria, which can start at a massive 10 million counts per 100 milliliters, are strictly limited to under 100 by the IMO, while our unit targets an exceptional level of under 10. Finally, the system tightly controls the pH range between 6.5 and 8.0. Every single parameter on this table in 7.jpg is fully compliant, proving that proactive mechanical management guarantees regulatory success. We wrap up this episode with our Superintendents and Chief Engineers Forum, as presented in this episode. Operational excellence is not a one-time event. It is maintained by proactive engineering supervision and continuous sharing of field knowledge. I want to hear from you. In your offshore experience and during your routine inspections, what has been the primary root cause of STP failures on your vessels? Is it chemical toxicity from accommodation cleaners killing the biomass? Or is it neglected blower maintenance? Leave your thoughts and experiences in the comments below. Let's start a technical discussion. Don't forget to like this video, subscribe to NEGM Marine, and share this with your crew. Thank you for watching, and I'll see you in the next offshore engineering episode.